sometimes it works better to do it with respect to y. So we can go either way. You want to do it with respect to x when you have problems where your starting and stopping points are on the x-axis. So I think like the last one, or next to last one, we did one yesterday that was like a semicircle type thing. And we started and stopped here, so we had clearly defined x values. You know, when we rotated that one, do you have a definite starting and stopping point for your y? No, because it changes depending on where you're at. You know, here the y values are different than here. But we had a clearly defined starting and stopping for the x. It was the height that was varying, not the length. When we do it with respect to x, then our cross section, we look at a vertical slice like this and base our radius off that, and we get an equation in terms of x. So if I wanted to do it with respect to y, we do that when, let's say I'd taken that same curve, but I rotated it around the y-axis. And so then I get something, this has a clearly defined height, but my x is different each place along that. So this one I would integrate with respect to y, and when I did a cross section, I would look at a horizontal slice of it. The premise though is the same. We'll integrate from the starting to the stopping, and it's the area of the cross section that we integrate to get our volume. So let's look at a problem. I want to find the volume of the solid y obtained by rotating the region bounded by y equals x cubed, y equals 8, and x equals 0 about the y-axis. So start with a picture. Y equals x cubed. Okay. So we should know generally, even without picking points, what's x cubed look like? That's just your chair. So it looks something like that. Without exact points. What's y equals 8? Yeah, just a horizontal line at 8. What's x equals 0? It's the vertical line at 0. If you wanted to find this intersection point, that is when x cubed is equal to 8. So that's when our x is 2. So in terms of my solid, I am taking this section right here. And I am rotating that. I could rotate it around either axis, but I'm telling you you're rotating it around the y-axis. So if you start spinning that around the y-axis, easiest way to draw a picture would probably just draw the reflection first. So if I just flip that over the y-axis, it looks like that. And oh, that's a horrible picture. And so we get this curved looking thing. Okay, it's kind of like a funnel with the bottom cut off. Okay. All right. Would this one be better to integrate with respect to x or y? Y, absolutely, because we have a clearly defined starting and stopping point on our y's. Okay, my x value varies depending on where I'm at on my curve. So we will integrate. If you're doing y's, everything has to be a y. So this is a y, these values have to be y's. So my starting point was when y equals 0. My ending point is when y equals 8. If we had been able to do it with x's, you would have stopped your x's at 2. So you just kind of have to depend on which variable so you hit the right limits. Then we have to do pi times times the radius squared, because if I'm looking at this, a cross section, if I slice it horizontally, my cross section is just a circle. So area of a circle is pi r squared. So the radius of this circle would go from the axis out, and the equation for that is y equals x cubed. But can I put x cubed in here? No. So what am I going to put in there? If you solve this for x, you would add a cube root. So we are putting in the cube root of y, because everything had to be in terms of y here. Alright, so I could pull out my pi. That's like a y to the 1/3 squared would be y to the 2/3. So if we add 1 to the power, it's 5/3. Means we need a 3/5 in front. Well, let's practice evaluating with no calculators. I think we need that. So if I would have 8 to the 5/3 minus 0 to the 5/3. That means the cube root of 8, which is 2, to the 5th power, which is 32. Cube root of 0 is 0, to the 5th is 0. So we get 96 pi over 5. Questions there? Alright, let's talk about this. So, every problem we've done so far, I know somebody pointed it out yesterday, when we were looking at our cross sections, everything we were looking at had a circular cross section. Now, it will not be the case that every single solid has a circular cross section. For instance, if I were looking at a square pyramid, so the base is a square, you're looking at that pyramid, would it have a circular cross section? No. So not everything has to be circular. However, if we take a continuous function and rotate it around an axis, you will create a circular. So if we just have a nice smooth curve and you start rotating it around an axis, it creates a circular cross section every time. And so we know that area of a circle is pi r squared. And in this case, if you're only looking at a positive function, when you want to measure the radius, the distance from the axis out, the radius is always the function. So on all the problems we've been looking at, it's just pi times the function squared. That's what's called the disk method. So that's what we've been doing. Everything, we're just rotating curve around an axis, so we create circular cross sections. The radius is the function every time. So that is the first way that we can calculate volumes. Now I want to look at a second method. So instead of starting with the formula, I'm starting with examples, and then the formula makes a lot more sense. I want to find the volume of the solid formed when the region enclosed by the curves y equals x and y equals x squared is rotated about the x-axis. So we have to draw a picture here. Okay, let's set these things equal, find these intersection points. So I need to know when x squared equals x. If you subtract over your x and factor that out, we get our x to be 0 and 1. Okay, that's where our things meet. We can draw it. Y equals X is just the line. Okay, you can certainly draw the full line, or you can only draw the part you need. I'll start by drawing the full picture just to illustrate it, and then I'll erase what I don't need just to show you what's going on. Y equals X squared, what's that the graph of? A parabola. Okay, so if you drew everything, my picture's a little off, but it looks something like this. Now, all I'm looking at is this little region right here, the intersection, the between 0 and 1. So that's all you really have to have in your picture. And if you have more, that's fine, but if you don't, that's okay too. That's the minimum. And then what axis am I rotating that around? The x-axis. So easiest way to draw that picture is maybe reflect it first. So the line come down like that. And then we have our curve, which if you reflected it would look something like that. So this is my solid. How is that different than all the others we've been looking at? If you take a cross section, what does our cross section look like? If I sliced it right here, what would it look like? A washer. It's not a solid, is it? It's circular, but you have the outside circle and you have the inside circle. It's like a donut. Okay, the center is hollow. So your cross section is not just a solid disc. Okay, we have an outside, we have an inside, and it's hollow in the middle. So we have to set this up a little bit differently. So we will integrate. Are we doing with x or y's on this one? X. We have a clearly defined start and stop for my x. So we're going to go from 0 to 1. It will be a dx. Okay, it's still circular, so that's like pi r squared. But how would I find, if I wanted the area of this little donut, how would you find that area? You'd have to subtract. You'd have to do the area of the whole thing minus the area of the inside part, right? You have to subtract that off. Okay. So area of the outside circle is pi times the radius squared. So the radius of the outside, which one is on the outside? The x. Minus the area of the inside. So it's a circle again, so pi r squared, but the radius of the inside curve was my x squared. You could pull your pi all the way out and get x squared minus x to the 4th. So the antiderivative of x squared would be 1/3 x cubed. Antiderivative of x to the 4th is 1/5 x to the 5th. So if we plug those in, we get 1/3 minus 1/5. When we put in the 1, minus, if you put in the 0, you just get 0. And if you want to do this by hand, you need a common denominator. What's our common denominator? 15. So that's like a 5 over 15 minus 3 over 15. And we get 2 pi over 15. Should you ever get a negative volume? So on these problems, if it turned out negative, what does that mean you did wrong? You switched them. You had the outside one subtracted off. Okay. So this is the second way of calculating volume. And this is whenever you have two functions that get rotated at the same time. So when you look at those, again, if it's a nice continuous function, just rotate around an axis. Your cross section, it's still circular, but you have an outside circle and an inside circle. So that's called the washer method, when you have to do the area of the outside one minus the area of the inside one. That is about as complex as we are going to get. These volumes, if you go on to take more calculus classes, you will get much more in depth with this. We are keeping things fairly simple with our examples. So either we'll have one solid or we'll have a cutout in the center and we have to subtract off. So let's just do some more practice problems for today. I'd like to do maybe a couple more and then give you guys time to try some homework. So let's find the volume of the solid obtained by rotating the region in the last example about the line y equals 2. Okay, so the example we just did, we had y equals x and y equals x squared, and we rotated it around the x-axis. I'm changing this. I'm rotating it around a completely different line. So we can start out with our picture the same. Okay, we knew y equals x was just the line, they intersected at 1. Y equals x squared was the parabola, so we had this little region. What's the line y equals 2? What does that look like? It's a horizontal line at 2. Okay, so if I want to draw this picture, so if I first just reflected this over that line, so think about just folding your picture on that line. There's your line, your parabola. So we get a picture like that. First question is, are we going to integrate with respect to x or to y? So to integrate with respect to y, you have to have a definite starting and stopping height. Do we have that here? No. Here it's from from 0 to 2, but here it's from 1 to 3. So I don't have a definite y. Do we have clear starting and stopping points for the x? Yes. So let's integrate with respect to x. Okay. My limits with my x's, my first x would be at 0 and we end at 1. If I take a cross section, we are definitely looking at a washer here, so we're going to have to subtract off our areas. So it'll be pi r squared minus something pi r squared. And if you prefer, just go ahead and pull out the pi and only write it once. You can do that. The outside radius. So the outside is going to the line. Okay, but this is not just going to be, bless you, y equals x. How would I get the radius here. It starts on my horizontal line and goes up to the x. What do you think? Any idea?
Is that picture drawn right?
I think so.
Wouldn't the parabola be on the outside of the top?
Oh, yeah. Wait. Hold on. Yeah, when I reflected it, I put my parabola in the wrong spot. Thank you. Okay, so if I measure from my center, you can go either way. If I go down, the outside is the parabola. Okay, if I just said y equals x squared, that would only take me up to here, wouldn't it? What do you want? You want to start at 2 and go all the way down to x squared. So what we have to do is 2 minus the x squared. 2 minus x squared would say you're going to start at 2, you're going to subtract off x squared, which would take you to here, and you get everything in between, which is what our radius turns out to be. Inside radius, that's just going from the line. We want to start at 2 and go down to the line, so we'll have to do 2 minus x. It definitely gets a lot harder when you are rotating around a horizontal or vertical line other than the x or y axis. You're not going to have any of those on your homework yet. You're not quite ready for those yet, but I want to go ahead and start talking about some of those together. So we had to take our starting point and subtract off the curve to get everything in between there. Are you guys okay with me there? So that's the hard part. Now this is integration like normal. So we can pull out our pi if you haven't already done so. I'm going to go ahead and FOIL. So that would give me a 4 minus 4x squared plus x to the 4th minus 4 minus 4x plus x squared. Okay, if I subtract like terms, my 4's cancel out. Then I have a negative 4's gone. I have negative 4x squared to negative 1x squared, give me negative 5x squared. I have my x to the 4th, and I have a 4x. So integrate. That would be a negative 5/3 x cubed plus a 1/5 x to the 5th plus a 2x squared. If you plug in a 1, negative 5/3 plus 1/5 plus 2 minus, if you plug in 0, you get 0. Practicing getting our common denominator so we can do these without a calculator. So that would be a 15. So we get 8 pi over 50. gonna do the other example, but I think I wanna stop and make sure you guys have some time. So we'll finish the examples tomorrow. I want you to add to yesterday's homework. So yesterday we did 1 and 3. Today I want you to do 4, 5, 7, and 9. And you have the rest of class to work and ask questions.